Good morning, good afternoon, good evening, depending on where you are. Welcome to the Friday weekly HSM Hangout. Today we have a very special guest that a lot of you might be familiar with. He is a level 70 machinist, Mr. Rob Lockwood. Rob, thanks for joining us today.
Yeah, no problem.
Excellent. So, to kick things off, Rob's going to be talking about toolpath tolerancing today, but to get a better grasp and feel for who we have in the audience today, I wanted to ask a couple questions. I'm going to start with one that we've been bringing up the last couple weeks. Have you been to Autodesk University? And the reason we're asking this is, CAM has become a big part of Autodesk and the whole make movement. And there's a large focus. In this past year, there was actually the first CNC course, hands-on course at Autodesk University. So we want to make sure that our community is aware of this and takes advantage of this fantastic event. So we've got about 50% voted. Let's get a little bit more here. So I'm going to close that and share the results. So looks like 14% of the audience was there, so we'd love to hear some feedback in the comments as to what you thought of the event, what you'd like to see more of. A lot of the group would love to go, would like to learn how to get there. The Past Fusion CAM Challenge that was available, and it's actually available across all HSM products, via Instagram, the award was actually a trip to Autodesk University, so stay tuned for more of those types of events. We do have some more people that don't like people and like making parts. So I'll show you at the end where you can access all the videos and all the content that was at Autodesk University this year. Okay, the next question, how long have you been an HSM user? So, we have the Wednesday weekly webinars that are intended for new users, but we have a lot of veterans here, including Rob himself. Looks like we've got a couple other level 70s here joining us today, which is awesome. A lot of users. Let's see. Thanks for voting so quickly on that one. We've got a lot of users more than 2 years, so it's nice to see an even split here. The community seems like it's shifting more and more to the veteran users, so people are adopting the software and using it, continuously. And let's see, what type of work are you doing? I know that we get some suggestions to update this, and we'll need to keep revisiting that as we get a lot in the other category. But it looks like we've got a lot of aerospace this week, a lot of mold shops, a lot of other. If you're placing other, can you please put some feedback in the comment section or in the question window? We'd love to see what you're working on. So about 60% other. So please, provide some feedback on what that other looks like so we can have a better understanding, and maybe we can update these specific categories, not too much in the automotive or mold shop sectors this week. And the last question is, what's most likely to drive growth in your shop? And we mention this every week, but this is really good feedback to provide to the development team. We've got development, people from the development team in the background here, and they look at this closely and they want to understand where you see your business growing in the future. So let's, we're about 50% right now. Let's get that a little bit higher. So similar to last week, we're seeing a little bit more with the turning. We didn't see really any turning a couple weeks back. So a lot on the 4 or 5 axis, and the turning, those numbers are continuing to increase. So that's really good to see. And I know our developers are taking note of that as well. So those are all the questions that I wanted to ask before we get started. So Rob, I'm going to pass it over to you, and I will let you share your screen right here.
Yeah, I think I should be good. That's me. Does that actually work? Am I up and live here?
Yep, looks good.
Yep, looking good.
So today I wanted to take a time to talk about one of the more common questions that I think is really hard to answer, and it's sort of what should I set my tolerance at? So today's talk is on tolerancing in Toolpaths. I'm mostly going to focus on them in finishing Toolpaths, but I think we'll have time to get into how it affects some of the roughing Toolpaths as well, and maybe solve some problems that people see there as well. So today, tolerance and how to make pretty surfaces in spite of it. So the first thing is sort of, what does that tolerance setting do? You'd probably have noticed it at the top of every single operation, I think, in HSM Works, in Fusion, in Inventor. And at least in all of the 3D toolpaths, I think its main purpose is to set the tolerance, the surface triangulation tolerance, which winds up being, so most of the surfacing toolpaths work from tessellated models that are STLs, and these are most commonly associated with 3D printers, and they're kind of well known for being dirty, and if a customer's ever sent you one to machine from, you've probably sent them back and said, I can't machine that and can't work from that and all of that stuff. And I think a lot of people maybe don't even really realize that they're working from a parametric, step type parasolid model in their CAD program, but that when you hit your generate button, it gets converted into an STL, and the toolpath is generated on that STL. It is not generated on that nice, perfect parametric parasolid model that is living in your CAD program. Instead, it gets sort of subbed out and becomes this, inherently dirty tessellated model. And we'll show that happening as we get going through here. But so what's the problem with that? Like I said, tessellated models are inherently imperfect. It's basically taking all of these crazy surfaces that you have that are that somebody spent hours working on making a perfect spline and making it look exactly the way they want. It just converts it into a bunch of triangles that sort of approximate and oftentimes do a bad job of approximating that surface. And the trade-off here is that you could get a really, really accurate tessellated model if you're willing to spend a whole bunch of time generating that. But generating a super accurate tessellated model, for one, takes time directly, and then the more accurate that tessellated model is, the longer the code takes to lay out on it, the more points that you wind up with, all of that stuff. So you have to sort of strike a balance between getting the accuracy right to where you have a tessellated model that represents your surfaces that you want, but that's not so overly generated that it kills you on calculation time or on toolpath output size. My picture looks like it covered up the bullet there, but that's okay. So in particular, this applies to projected and sliced toolpaths. So those are that represents the vast majority of toolpaths that are in the Autodesk HSM software. That includes everything from contour and ramp, which are both sort of these slicing toolpaths, to project and parallel and spiral and scallop and all of the other toolpaths that are projected from some viewpoint. And we'll look at some of the differences there and how it affects those differently too. But moving on. So what should I set my tolerance to? Like I said, this is probably one of the more complex questions in CAM, and I think it's as convoluted as what speed and feed should I use. And if you've ever really sat down and tried to figure out the answer to that in any given scenario, it's like, geez, that kind of depends on everything. In this case, it really depends a lot on the operation surface requirements, and so what that means is you'll wind up with a totally different set of, or you should wind up with a different answer for a roughing operation compared to a finishing operation, and even within that finishing operation, depending on how perfect you want that surface to wind up and how well your machine does handling. Once you get into a certain level, you start having other issues. So the machine tool itself and its dynamics and your feed rate expectations. Obviously, if you start generating this too finely, you're going to get an output at the end that is just a million tiny line segments, and different machine tools will handle that differently. And that's going to depend on the machine tool's look ahead and also smoothing capabilities. And we'll talk about smoothing too. That hits on there's a couple different forms of smoothing. And all machine tools have this sort of speed, accuracy, and smoothness balance. It's kind of the race car problem, and I think we'll get to that too in a second. So what about smoothing? Can't I just use smoothing and generate this sort of dirty toolpath or this dirty tessellated model using a loose tolerance, but then use smoothing to come in and help it out? Like I said here, smoothing can be helpful, but it has limitations. One of the biggest ones are that it's really only useful in a place where the toolpath lies perfectly on either an XY, a YZ, or a ZX plane, and even then, it's only viable where arcs can be fit in place of, not just arc segments, but line segments. It also adds just an additional error into the toolpath, and even with all of that, some controls just don't really like to try and they'd rather have a series of line segments rather than arcs changing to lines or non-tangential arcs, which is what you get a lot from smoothing algorithms. And I think I'm sort of jumping ahead a little bit, and I've covered some of this as I'm talking, but so why don't we just turn it to 11 all the time, right, and just generate this super accurate thing. So this is a good demonstration of the race car problem. If you prioritize speed, it's going to come at the expense of surface finish or accuracy, and the same is true on any corner of this triangle. You might think that accuracy and surface finish are more directly linked to each other, but they really aren't. If you figure that the machine has to hit every single point that you're telling it to, then it's going to need to slow down and stop and make sure that it's perfectly following those line segments, and that is probably not what you want for surface finish. For surface finish, you really want smooth, nice transitions between those line segments, and oftentimes that means doing sort of a blend that smooths those out. This is a thing where a lot of the time you wind up kind of stuck, because if you paid attention when you were buying your machine tool, you might have, and this is something that you cared about, so it should have been something, if you cared about it, that you paid attention when you were buying your machine tool, then you probably went for something that had good capabilities for handling this situation. And one of the trickier, or the good tricks to figuring those out is just browse through the manual and see if you see this triangle in there somewhere. I think it's some representation of this triangle will be in your manual for every machine that's capable of doing high quality finishes, or that's sort of designed for mold making. And these will wind up being it's sort of different things. You have Fanuc has a nano smoothing, which is their high-end version. On a Heidenhain, you have cycle 32 or cycle 311 on some. And basically, they're just giving you different ways of prioritizing these, and that's really the important thing, is that if your machine tool can do a good job of handling the priority and is designed to sort of handle this scenario, then the answer is you probably can basically just turn it to 11 all the time. You can just say, let's output a really accurate stream of code almost all the time, you know, barring calculation time and file size, if those two things aren't also an issue for you. But then you can just turn it up, and then you can allow the machine tool to sort of sort out what priority you want. So that's something that I would suggest if you're looking to improve your surfacing and you're able to buy new machine tools, or haven't looked into this on your machine. The more granular control you have over this aspect, the less you'll actually care about this whole thing, because you'll just be able to kind of ignore it and just over-generate the whole time. So that's all I have for slides. Let's jump into HSM Works and actually start taking a look at some of this stuff, and hopefully this will be better. I've got this nice upright that we'll use a little bit later, but I'm going to start just by making a brand new document. I'm just going to sketch basically the simplest part in the world. And we'll say a 2-inch diameter circle. And I'm using HSM Works today in SolidWorks, but this is really, and this isn't just consistent across all of the Autodesk CAM platforms. This is consistent basically across all CAM. They all work in the same way. You'll find different ways of handling it, or of viewing it, or small differences like whether or not the tolerance is only plus, or whether you have control over whether the tolerance is plus or minus. But what I'm going to do is just show, we're just going to show what the tessellated model looks like under some various conditions. So I think the default tolerance in here, I'm working from a pretty bare bones, like fresh install of HSM Works, so most stuff should be pretty default. And 4,000 is simply, it's too big for, I mean, if you're a machinist and you're machining parts, you can't work from a surface tolerance for finish of 4,000, so I'm not sure why that was set. Okay, so I set this to a gigantic, totally crazy 50 thousandths tolerance. And what I'm going to do is, I've already got beta mode enabled, but if you hold Control and Shift and right-click in this open area, you can enable beta mode. I'm not actually going to use any beta mode functionality. I just want to show you that it exists and then use it to jump into this intermediate folder. And so when we generated this, we'll see if we can see it in Task Manager. it's too fast on this. Somewhere in there was a step that said generating offset surface or something along those lines. But so what I did is I jumped into this intermediate folder, and that's this is a folder that HSM Works uses. When you generate a toolpath, it dumps all of the information into here and sort of uses this as a temporary folder. What we care about is that it output this stereolithography STL. I'm going to make a copy of it because HSM Works doesn't like sharing, but then we'll just bring this in here directly. We'll look at how terrible that looks because I gave it this gigantic tolerance. This is going to be really useful for demonstrating one of the more common issues that you see, and I'll try and demonstrate that now. So probably if you were programming this part, you'd be looking at maybe surfacing this upper area, but you probably would want it trimmed up nicely so that the tangency of the tool just comes down and just kisses this edge perfectly. And toolpath tolerance is going to make this pretty difficult to do, even when we go to a fairly small, actually, regardless of how small we go. What we're going to do is we're going to say we want to stay within this boundary. We're going to use contact point boundary to allow this boundary to define the point where the tool, the contact point of the tool is allowed to go. And so we'll just hit OK. And we increased that a bit. What we get is this really, I mean, that's just a terrible looking toolpath, right? It looks awful. And you're probably wondering, like, why did we get that? We have a pretty tight tolerance. The first thing to keep in mind is that what I selected as my boundary does not get tessellated. It does not have that tolerance applied to it, or at least not to the same degree. I'm sure that somewhere in the system it takes that circle and turns it into something other than a perfect circle. But you can see what happens is it's dipping down. And why is it doing that? So I think this is a good way to demonstrate it, which is that if we come in here and we do a sketch, and I do it on the correct plane instead of that one, I just draw a circle. We come in here and we say that this circle is at the nominal size, which I'd love to be able to just actually tell it 2 inches, but this diameter is scaled. But you can figure that it's somewhere about like that. And the way you can tell is because the tolerance that we're applying is positive and negative, right? And so you can start to see where if we're containing that tool point within this, there are sections of it that are missing, right? Where the tessellation of the model is basically causing the model to pull inside of our boundary. And what happens then is when we generate our toolpath, for most of it, it's laying on the surface, but in some places, the contact point is allowing the toolpath to drive all the way down, the boundary, the combination between those things. So what we want to do, what we probably want to do, or how we can sort of trick this, is we want to offset this, probably by our tolerance amount, or maybe slightly more, to try and keep that tool in contact with the model rather than diving down. And this kind of feels like a little bit of a hack at the start when you first come across this, but when you realize that it's basically what we're doing is we're telling it that we want our boundary to contain it to the minimum size. It's basically pushing all of the tolerance onto one side of the spectrum, if that makes sense. So what we can do is we can come in here and we'll just say this additional offset, we want to shrink that boundary by, let's say, the tolerance times 1.1. And I was able to do that because in all of these CAM, every parameter, right, if you hold shift and mouse over it, you'll see where it says parameter name. Every dialog box has that parameter name, and you can pull those in and use them as equations. But what you might have seen is that we got 1.1 times the tolerance in here. So let's take a look at this, and we'll see if it gets better. It got quite a bit better, right? Now we got rid of all of those spots where it's diving. And we got pretty close to the desired result, right, which is that tool is fairly close to the contact point. I mean, we're still working with a pretty loose tolerance. A tolerance of 1,000th is pretty high. Let's go. I tend to work with a tolerance of 2/10. It usually gets me into the ballpark for my machines and does a pretty good job. So we'll see how that looks. Much better, almost perfect, right? And we've got a pretty decent toolpath here. We maybe don't want it to hit the top of this. There's a whole bunch of stuff we could do to get rid of that. For instance, we could either tell it that the top is from the model top minus a little bit. We could give it a slope containment and just tell it to stay 0.1 off. Right? Any of that stuff would probably work. so that's one portion of it. I'm getting a little bit ahead of myself here. Okay. We'll go ahead and jump into this actual model. Well, the other portion that's going on here is you can see that when we made that change, this section up here sort of started getting a little bit worse looking. Let's undo it and go back to how it was originally and just compare the two. So this one's actually just it's a downside to how Scallop works, especially in combination with the contact point boundary option. If you look at it, I think it's the only one that has this machine areas using boundaries option, and that's forced on once you enable the contact point boundary. And what that does is it takes, and after all of your containment methods are put in place, it takes the boundary of where the toolpath's being allowed to go as sort of the final thing, and it uses that as an offset, and it applies some smoothing because that can kind of be dirty as well, right? It's being applied to that tessellated model. And so what you get, and we'll get the same thing, I think, if we grab this. Yeah, so we'll just get some dirtiness there, right? That's the same deal. What we're winding up with is because of that option, it's telling, it's the boundary then becomes limited by or becomes subject to that tessellation. In Scallop, there's some fun stuff we can do to sort of get around that as well. That's, again, I think still covered under the purview of this because it's a negative thing that's happening because of the tolerance. So in this case, what we want to do is actually just totally get rid of all of this, all of these options, and what we're going to do is just use. We're basically telling it now all we want to do is use the actual perfect circles as the boundaries to generate our toolpath, and we'll generate this, and what we're going to get is something that is probably draping this whole thing, but that generated some nice clean code, right? All of it's nice and smooth and looks nice. But we don't, like, the whole purpose of this was we didn't want to be touching this this top surface, and we don't want to be touching this area. So from there, I mean, that's just a way of getting nice clean output. Then you can use other methods to contain the toolpath. One that I like to use here is check surfaces, but with touch check surfaces enabled, which at that point what you're doing is saying, we're still going to generate that exact same code that we used, or that same toolpath that we just showed a second ago, but we're going to come in and after it's generated, we're going to trim it to only use sections where the tool is in contact with that surface. And in this case, we're still going to get the section that's lower because the tool, if we simulate, the tool is still in contact with that surface, right? It's a 90 degrees. So this one really works better on stuff that doesn't come all the way down. So because that's still in contact, it's still going to drive those. So then you have to add in a second method, like that's where the slope confinement becomes pretty good. And we'll see if we get something super clean here. Usually this works pretty well, but sometimes you'll get a little bit of a fragment. So anyway, I mean, that's for fillets. This is a pretty good option, right? It got us something nice and clean. Oh, excuse me. And let me grab some water. Yeah, it got us something nice and clean, and this will really handle most of your fillet stuff pretty well. I just want to take a second too to show that this is pretty applicable, and the same thing happens across all of these projection type toolpaths. If we just come in here and we generate using the standard settings, we'll enable contact point boundary. We'll probably get something that looks a lot like the scallop and is driving down and over that section. Right, we're getting these areas. It's a little bit less prolific, but I think it's purely because there's fewer passes. I didn't generate it with the same step over. And if we do the same, and you can see that there, that was with a totally different tolerance. Originally I was using 1/10. This time I'm using, I think it was 4/10. So we wound up with a little bit more than 4/10 negative offset. And it's that same deal is going to apply across all of these. Now, I think to demonstrate the negative of increasing tolerance to handle this, we can enable tool points. And let's just duplicate this, and we'll do a second version with that, we'll say 5/10. You'll see I altered that 5/10. Oh, excuse me, this isn't going to work for that one. Well, yeah, well, it'll work just fine. Just didn't work for my demonstration. I wanted to show that the offset would also update because I changed this tolerance. As you can see, there's considerably more points shown on the initial scallop. And what I want to take a look at is the smoothing. So let's go ahead and take the one that has more points. And you might think that I can enable smoothing and just get this toolpath to decrease in size. And we'll leave it at the default. That should be basically fitting an arc in anywhere that it can, anywhere that an arc exists. And in fact, we'll duplicate this again just to show our code size was 169 kilobytes. I'm betting that doesn't change at all. That changed a little bit, and it's probably because it was able to fit an arc in some place. But overall, I mean, that's not a very large. Oh, there you go. I think it was at the very top. Yeah, the very top where it's planar, you can see that it's able to remove some of these because those arcs fit. And this is a fairly flat toolpath, right? Like these are close to being on plane with the XY plane, but they're not. So, and they're not within the tolerance that we're giving to that smoothing algorithm. So it's just not really able to fit any arcs in there. I hope that's making sense. And versus a toolpath like Parallel, we'll see a much better utilization out of smoothing. And we'll just do the same thing. And you can see there it was able to eliminate a ton of passes, right, or a ton of points. And again, I don't remember what the initial was. We'll come in here and we'll disable it again just to take a look at it. Right, so on a toolpath where the passes are aligned with a plane, like these ones are, they're being aligned with X, they're lying on the ZX plane, right? In that case, it's able to find and do a great job of reducing. And on a lot of machine tools, this is probably what you want. If you look through that manual and you don't find that triangle in there someplace, this is most likely going to be your answer. This is going to give you something that is so basic in its output that your machine tool will be able to find a smooth, fast, and accurate method of driving through it. But that's just so it's really just so limiting in how often or how applicable that is to getting the ideal toolpath. If you can imagine how much of a restriction that is, if your goal in making your toolpath is to have it leave an equal scallop and follow the contour of the surfacing, and the surface, like in this case, isn't all aligned, like the center sections here are aligned to the curvature pretty well, but as we fall off this edge, they're really not aligned to the curvature. And this is on a round part, right? So it should be pretty simple, but it just isn't really, it really isn't very flexible. So you're just better off to look for, if you're interested in good performance everywhere, to be able to output something that does have a bajillion points here, but that the control can actually smooth and make it nice. Okay, so I think that's a good primer on a bunch of this stuff. Hopefully, I know I've been rambling. I haven't done a great job of preparing this week, but let's go ahead and get rid of that. Don't need to save that. Well, let's jump into this. I showed a picture of this. This is some FSAE upright that I pulled off of GrabCAD. So, and I think it'll do a good job of showing some of the really tricky portions of getting clean toolpaths just in general. So my first bit of advice is to try and align your toolpaths with the existing curvature, and oftentimes that means splitting them up. Even when you know, in the ideal world, you just throw one toolpath at this whole upper surface, and you'd get finished down to this bottom of this fillet all at once, and life would be great. But let's give that a shot, and we'll see if it works or not. Grab that same tool. And I'm actually going to jump out because when I made this job, I apparently didn't align Z. All right, that should be better. And obviously, if you were machining this part, you'd want to spend a whole lot more time in there doing your setup. All I really care about is that my Z is aligned because I'm just generating toolpaths. So let's pop in here. We'll grab that same ball end mill. You can see in there that I do have, this is a representation of the spindle housing. That's really handy if you're using shaft and holder, but I don't think we're going to get into that too much today. All right, so let's go ahead and try and just machine this whole top surface. And we're going to say, we're going to grab that, and well, then I'll do a better job of grabbing some of these. This one's going to take me a second to select everything. You can see I'm just working my way around. I'm allowing it to follow, using tangent propagation and propagate along Z. When I made that was my last selection, and it can follow a tangent line all the way around, wrap around, until it hits the next point where it doesn't know where to go. And so if you're just watching where that's at, you can see it's made it all the way around. That's going to be my next selection. Okay, so now we have something that's pretty representative. We probably want to grab and get rid of some of these interior sections. So let's say we wanted to do a scallop that just covers all of that area. We'll do all of our little tricks that we just did. We'll set this to something reasonable. Set this to something that should calculate okay. And we'll subtract by our tolerance times 1.1. We'll enable contact point boundary. Those are going to be all the changes that we'll make, and we'll see how this turns out. So right there, you can see exporting surface for tolerance, and it showed the overall tolerance. I think it was 0.05 millimeters. Okay, and so we got something that's workable and maybe is usable out of that. You can see it's not doing any diving down. Oh. I'm on a pretty old PC here, so forgive me if I managed to make this crash. I'm working from my old personal PC. But what you're going to see is that this is going to want to dive down into these sections in a lot of places. Particularly here, you really probably want this aligned so that it's traveling along these walls rather than down in. Right, if you look at how the tool is coming through here. And that's because this toolpath scallop is awesome, but it works by collapsing the outside boundary towards the center. And you can see that's probably going to work really well. We'd get a nice collapse through a lot of this section, but it just doesn't even know that this curvature change exists, and all that it does is tries to lay more toolpath onto it in the places where it's going, where the slope increases. It's doing a pretty good job of actually hitting this outside. This model's not exactly perfect. There's sort of a sharp point there, and that's showing up in our toolpath. That one's just a little bit wavy. Okay, so what can we do? Let's divide this up a little bit. I think we can still use that same boundary, but let's just get rid of the center section. Let's see how that turns out. We might also want to actually remove the fillet and do that as its own operation as well. Yeah, so now it's following that much better, and I think that now we'll come in here and we'll duplicate. Let's grab that one. And this tool is clearly a little bit big to get in some of these areas and even really to get any definition out of some of this. Actually wondering, I think I selected the wrong. Go grab that boundary. Yeah, because that matches what we had selected the first time. Right, so now by just doing that split up, yeah, our toolpath is a little bit more disjointed and maybe has a couple more lifts to it, but by splitting that up into two separate things, our toolpath is just going to do a much better job of following that contour, and it'll be much gentler. Okay, so one thing is that where does this sort of start to not work as well? If you noticed, all of the projection-based toolpaths are kind of going to start failing, or I shouldn't say start failing, but where they're going to have trouble is where they start approaching areas of high slope. Scallop does probably the best job of mitigating this, but it's still not immune to it. So one thing I'd like to say is that if you're able to, and you say you have a 5-axis machine, which I think if you're machining this, hopefully you do, or maybe you're just planning on doing it in a whole bunch of operations. But the thing that you want to try and do is isolate sections so that you're projecting the toolpath onto them as though they're low slope. And hopefully that makes sense. We did that with this upper section, but if I come in here and I try and machine down to this section, and we'll come in and we'll make a reference plane. We'll get this to where we can just barely see into that pocket. That's really not a great example. Okay, guys, I'm having a little, I think my SolidWorks is, oh, never mind, there we go, came back. Yeah, okay, let's take a look at one of these. If we come in, there's some position where we can see this fillet, and it's going to want to fall off of the edge of this the surface. If you can tell right here, we can see, let's say, most of this. And we need to make a plane. And so I'm just going to use a view plane. Basically, this is not very parametric, but it's just I'm looking at this surface. I select a point and I say, let's grab the screen orientation, and we'll use that to create a plane. And that way I can come in here and we'll say we're just going to machine these couple of surfaces here. And we'll be able to tweak that, and that's kind of a useful thing. And so let's grab these as a boundary. Grab our tool orientation first. I've done such a good job with making this toolpath that it's just not really going to fail on me. Let's instead start taking a look at some of the roughing issues and where tolerances sort of apply to that. I sort of glossed over some of that, but let's generate an adaptive clearing operation, and we'll see some of the places where tolerance starts to factor in there. Obviously, on a roughing operation, we probably don't care too much about making sure that the geometry that exists when we're done roughing this toolpath or this part out matches perfectly. So we're willing to give up probably quite a bit on our tolerance in order to get generation time and hopefully code size down, and maybe get that generation or that toolpath execution on the machine kinematics and its sort of performance to increase, right? We're willing to maybe use a 4/1000th tolerance. Let's just go ahead and do the Tim Paul here. We'll just jump in and hit generate, and we'll see what we get. And then I'm going to try and force it into creating some moves that I'm going to force it, but hopefully people have seen this happen and maybe didn't know why, or didn't quite understand why it's why those extra moves are happening. It oftentimes crops up in two scenarios. One is when your stock to leave gets pretty close to your tolerance. And I should have just done it that way to start with. The defaults are really pretty good if you're leaving the stock amount is sort of close to the default and the tolerance is close to the default. But if you it's pretty likely that you probably have jumped in there and altered the stock to leave amount without changing the tolerance. And you start to see things like this, where like this is a vertical wall, and if I had left this open, or if I had left the original, I don't think I'm going to bother to recalculate it, but the original settings were pretty good because we were leaving 20,000 stock, and so there's a good margin between the toolpath and the tessellated model. This is a vertical wall, and so we really shouldn't be winding up with these additional step ups. If you picture that this tool, it already came in and got that section, right? It already roughed that. But that's just a result of the same thing. It's the tessellated model being dirty, and we went in and machined up to that point. But you have to remember, this isn't the model that the toolpath is seeing, or that the algorithm is seeing. It's seeing that tessellated model, and so if that's dirty, you're just not going to get good results even out of a roughing toolpath. This is a place where I like to leave about a 4-to-1 ratio between stock to leave and the overall tolerance. We'll see if that gets rid of these. Sometimes this takes some tweaking. And there's a little bit more you can do in a rest roughing case. And we'll take a look at that next. But hopefully this will just show that you want to maintain that sort of 4-to-1 ratio or somewhere close to that. But as you can see, I decreased that tolerance, and of course it's going to bite me, and I'm not going to get quite what I'm after here. So as you can see, we're still getting quite a few step-ups there. And actually, I'm not sure why that's happening. It did a much better job as we got further down. I'm wondering if that's actually not vertical there. They shouldn't be using somebody else's model. But as you can see, changing that tolerance, it did directly impact my calculation time. We're now spending, I should be actually looking at the numbers, but probably close to twice as long generating this as we were the first time with the 4,000 tolerance. And it's not really giving us any benefit unless we can get rid of some of these moves, which just seem to be persisting on me. This is not going super well here.
So Rob, you might think it's not going super well, but the truth is there's lots of comments saying they're enjoying watching you work through the process. So it's very good to see how somebody that knows the software as well as you do thinks through it and gets through the problem. I'd say it's an excellent learning for all of us.
Yeah, but we'll see if I can get through the problem or not. This one might just persist and kill me. I didn't know you were on here. You have any advice here? You gotta.
So I'm actually, for those that are interested, I'm at Pier 9 getting some stuff set up. So there's actually myself and Mark Porsby and CJ and Angelo and George and a whole bunch of us in the room here.
Oh, very nice. Great audience to be.
Yeah. Awesome. If it were, the one little trick, if it were not an adaptive, you could use the toolpath trimming and manually chop it away. So it's just a little trick for people that might not have known that.
Yes, yes, and that is a great trick.
Can't do it in Fusion.
So I'm just basically going to assume, and I'm not going to take the time to prove it out here, but this is an area where those should be going away. I'm going to blame this on this coming from somebody else's model, and I don't know, maybe that's a load of bull, but usually the trick is, as long as your tolerance is within about 1/4 of your stock to leave, you just won't get those moves. I have seen a couple instances where these have cropped up and I've complained about them, and they've always promptly sort of gotten fixed, and I suppose it could be the case that I'm sitting on one of those versions on this old laptop that just...
Yeah, either way, send us the file. Martin, who incidentally is the guy that works on Adaptive, he always loves getting the files. So.
Yeah, nice. Okay.
People might think they're being rude reaching out to the developers. There's nothing developers love more than to see their product in use and have specific cases to build around. So feel free to share it.
Indeed.
That was Mark saying indeed. He runs the UX development team.
Nice. And I'm going to go ahead and move some of these past so that I can do some I can change this into an actual rest roughing, and we'll see if we can get some of that same dirtiness. I think I'll have a little bit better success here. So we're going to tell this, rather than coming from the job stock, we're going to look at the previous operation. So now that's saying whatever is left. You can literally imagine, actually, let's even jump in. So I'm showing the operation IDs. Let's jump back into this intermediate folder, and we'll see. So you can see this is operation 6. A sort of a nice little trick here is that it does also, you'll notice that this operation has 2 STL files that are being output. I think this one's not quite done generating yet, and so we're still showing a 1 kilobyte file there. Yeah, we'll give this a second and let it generate, but we're still getting that output STL that's being used for generation, but we're also getting a second one that's the stock that is being looked at. And because this is rest machining, that's basically the stock that exists at the end of this operation. And I think that still succumbs to that same tolerance in the operation, and there might be a little bit more in there. We'll see if we can get this to finish up. What did I give you for a tolerance? I give this a pretty tight tolerance, and that's probably a good reason why we're seeing so much time being spent on generation here. I really don't want to spend this whole time just sitting here waiting for this operation to generate. All I was looking to show was that this does generate its sort of the stock model in here as well, and you can pull that in and take a look at it as well. And that might be a good way, or that is a pretty good way of if you're having issues or wanting to know, not so much in the sort of dirty little extra move stuff, but if you're just getting behavior that you're just not sure what's going on, oftentimes you can pop in, take a look at that model, and it'll just be like, oh, I've just still got a whole bunch of material over here that I didn't realize, or that a lot of stuff like that. It's pretty useful to just directly be able to see what is being used by that operation and kind of what, oh, and there we go. I'm being foolish. Here we go. Here's rest for 6. So we'll make a copy of that because HSMWorks doesn't like sharing. We'll bring this in and we'll see what it looks like. It should basically be the exact same thing as if you simulated that adaptive 1. We'll get something that, but the difference is we're getting exactly what this operation is seeing when it's going in and searching for stock to remove. And it's really a similar thing as if you had just brought in this STL and specified that as your stock for the operation, right? Rather than looking at the actual stock that you defined in the operation, now it's just looking at this. And you can see my performance is really going pretty bad due to the calculations that's going on in that other model. But anyway, that's just a nice thing to be able to take a peek at and see. This is like a good instance where sort of if you were using this as rest machining from the second operation, it shows kind of, you'd be seeing all of this extra. So you'd want to do an operation that removes that cap off of the top first and then start doing rest machining off of that. Yeah, I'm just going to end this. This is taking way too long.
Hey, Rob, I had a question here, sort of thought anyway.
Sure.
We're coming up on time. There was an earlier question as what machines you use, and that kind of reminded me of the work. I think it was Jared who you worked with did it, but I remember him doing some tests on what the best tolerance was for his brother. And so when you mentioned what your default tolerance was, that's when people were asking about what machines you had.
Oh, sure.
You can speak to a little bit of the testing and how you found the right recipe, if you will, for your machines and how Jared did. I think that might be helpful for some people on the call.
Right. I can talk. I don't know how much I'll be able to do to show too much of that, but I can certainly talk about it, and we'll just
some things for people to think about. I think would be great.
So the machines that I'm currently running, I'll just go through and I'll give a history, and I'll talk about kind of the difference or what I've come across. I started off running Fidal machining centers were pretty much all I touched for the first year or two. And they definitely fall into the category of, if you look through their book, I don't think that you will find that triangle anywhere in there, and I don't think they had really a whole lot of, I think they just branded them as high-speed machining centers and thought that that covers, you know, everything. It says it's a high-speed machining center, so we're good to go. And honestly, at the time, like, there wasn't a whole lot of this going on, at least not on commodity machines. So then I eventually graduated to some Morisiki sort of Dura centers and Dura verticals, and that was my first instance of, after fighting for years, doing everything I possibly could just to keep code size down in order to get the code to run properly at the machine. This was the first step into having some ability to deal with code at the control. And that was the first time that I really went through and did any calibration of trying to figure out what the best tolerance is and what the output should look like, and then what you can do at the machine. But what I will say, on those machines, they didn't have the greatest look ahead. They kind of were, I think, in a similar position to what a Haas control is right now, which is you can sort of give it some level of priority, but it's really it's not very granular. You're just kind of telling it, hey, I want to go fast, or hey, I want to go slow. And that augments the acceleration and deceleration curves, and you still care about tolerancing, but not maybe to the same degree where you're just pulling your hair out trying to get everything to be perfectly smooth coming out. So at that level, it helps a lot. At that level, you probably can say for tolerancing, or for surfacing stuff, you want to be 4/10, and for roughing stuff, you want to be 2 thou, and then you throw out kind of an M code, or I think that on that machine it was a G332 with, you know, a parameter of like 1 through 4, and 1 was accurate and 4 was fast. And if you were running something that you cared about the surface finish on 4 you just blew through all of your corners and kind of undercut everything and gouged all over the place, and it was awful, and the vice versa was you just go super slow when you're trying to just remove material. So where I'm at currently is on we have 2 machines that use Heidenhain controls. Both of those they basically just want a really constant stream. And how we arrived at that, and when I mean constant stream, I mean they just want you to give them as many linear points as they possibly can, and it will go through and determine a spline throughout it. You still have to give it some priority, or you still can give it some priority over smoothness, accuracy, or speed, but the code output really wants to just be the same. The things I would suggest to do for testing some of this is literally just take a pretty basic surface that represents, you know, that initial fillet thing was pretty good, and output the code the way that you, or output the toolpath the way that you would run it. If you frequently just do sort of XY planar, if you think like waterfall or contour type toolpaths, output the code like that and take it to the machine and run it in, you know, do test blocks. Run 5 different parts that, you know, one that has a 2/1000 tolerance, one that has a 1 thou, one that has a 5/10, and one that has a 10th. And see, you know, sit there with a watch or a stopwatch, time the parts, and then when you're done, mark which one was which and take a look at it. And do the same thing if you have the ability, if you have those you know, G187 codes or G332 codes, do the same thing on each one of those. And this takes time, but it's a really, really good time to spend, because if you record those values and you sort of carry those forward and just know that if you have a similar surface and you want a similar quality, and you know, then you have a baseline to work from. And we have 2 machines that have Heidenhains. They're both, the controls are nearly identical. The machines couldn't be further apart. One of them is an ultra lightweight, high speed. I mean high speed in the sense of linear motors and everything on it is sort of light duty, and it's an incredibly fast machine. The other one is sort of the polar opposite to that, which is that it has ball screws and is a hyper accurate machine. I mean, both of them are hyper accurate, but it has mass to everything. And even with the same control, they both react completely differently, and it takes 2, you're just looking for 2 sort of different pulse streams coming out of them and feeding them the results of those tests are just different between the 2. I just basically can't stress enough how valuable the time is to figure out what your machine wants and just and knowing how to give it that. It's just
I think that was
really well with it.
super helpful how you mentioned you've got two machines with the same control, but how you treat them is slightly different because of other factors. So the time well spent to just make some part and figure it out on each machine that you've got.
Yeah. Yeah, and I would say that's incredibly true across a lot of the sort of FANUC options as well. You'll see, there's probably 150 different machines that have the same exact FANUC 31i, and one of them is going to be a Doosan that's just sort of a commodity machine, and one of them is going to be a Yazda. And the big thing between the two of those is largely in how much time they've put into making that control perfectly match, the weights of everything that's in it, and just having everything be perfectly dialed. I mean, there's more to it than that too, but that's a portion of it that's not to be underestimated. Is the difference between an awesome machine and a less awesome machine is often in how well controlled all of that stuff is.
Excellent. So I think this was an amazing webinar. Thank you so much for talking us through it. They've got nothing else.
No, I'm good. Yeah, I'm good.
Very, very.
Yeah,
well.
Rob, we had a lot of.
We watched that.
Exactly, a lot of great comments saying you were really teaching them things, and these are things that owners should know of their shops, and really, really useful stuff.
Well, that's great to hear.
Yeah, cool. Thank you. So I'm going to take over the screen here then in that case.
Sure.
And just end it off. So we want to give a shout out to Rob. Lots of great feedback in the comments here. So follow Rob on Locktool or on Instagram at Locktool. One thing I wanted to make everyone aware of, we've got some exciting events actually coming up for the weekly hangouts over the next couple weeks in the Boston Build Spaces. So I know we talk a lot about Pier 9. Here's some images of that. There's actually a CAM Summit going on at Pier 9, and next week's Friday hangout will be live from Pier 9. And the attendees of that summit will be the development team, the support team, the applications team, all the people that are making HSM so great for your applications. And Al, maybe you can touch on this, but I believe you're going to be doing a summary of that summit during next week's hangout.
Yeah, so we'll have a bunch of machines set up. Matt Searle will be running things, the DMS, the Haas, some stuff going on the water jet, so we thought it'd be a good opportunity just to kind of do a live tour, if you will, through the shop next Friday. And then I think following that, just keep an eye on our YouTube channel, because throughout the week I will be recording a lot of the content, so that even though it's just employees here, I will see if we can't make that available to users wherever it makes sense. But Friday will be a live walkthrough and maybe an in-person or at least a digital introduction to many of our developers that will be here for that week.
Awesome. Yeah, so stay tuned for that. Invite friends that you think might be interested. We talk about Pier 9 being this fantastic space, so it's a great opportunity to get some visibility into there with the team. But besides that, are any other questions or anything that comes up? If you have interest in presenting a topic, I know we've got a lot of level 70s on here with us, or if you have suggestions for future topics, reach out to Wayne or myself. And other than that, everyone have a wonderful weekend, and we look forward to seeing you next week.
Thanks, guys.